thanks, Peter and Benoit, for inviting me to this beautiful conference. I mean, 30 years, that's quite a long time. And I remember very well when I started this. Actually, I went to Berlin in '83, so 31 years ago. And at that time, it was this person who did many pioneering work in the field of these colloids. It was Arnim Henglein, and he was a radiation chemist. So I came in a group, it was radiation chemistry, and you may ask, what is radiation chemistry? How is it related to quantum dots? The story was actually that these people from radiation chemistry, they investigated radical reactions, mainly initiated by gamma irradiation, which form hydrated electrons or OH radicals in solution. So it was the reaction between hydrated electrons and many, many different materials which were investigated. So they investigated also inorganic substances like silver, ions which become reduced by one electron to a silver atom, and then many silver atoms come together forming silver clusters. At that time, they saw already all these things changing redox potential as a function of size. And finally, if everything is consumed and you have formed your colloidal particles, then the electrons charged the silver and hydrogen was evolved. And that was just during the time of the second oil crisis when they did this. And people were thinking of how to make artificial hydrogen. And that was the beginning then, how this field merged together with people from photoelectrochemistry, who of course did not use gamma irradiation. We don't want to have gamma irradiation to make hydrogen, but used solar light. And then that was the beginning somehow at this point where people tried to use with small semiconductor particles to make artificial photosynthesis. And then the idea was actually, many people used suspensions, and the idea was, let's make them smaller. Smaller because then the charge carriers are immediately at the surface and they can do the catalytic reaction. And by that, there was really a magic time in a way that people making cadmium sulfide, they were discussing, oh, my cadmium sulfide is a little bit more greenish, the other is more reddish or yellow, and didn't know what to do. I remember that a postdoc from Michael Grätzel's group came to us and he said, oh, he overthrew away a solution of cadmium sulfide because it didn't turn yellow. And then it took some time, and Arnim went to the US and met you, Louis, and you were discussing these things. And then we know what is going on. This is the quantum size effect. And here is actually one of these first works. So this is the beginning of the cadmium sulfide work by Henglein in '82. And then in '84, you see already here, that's when I also entered this group there, the world of the neglected dimensions and small zinc sulfide particles with quantum size effect, and here cadmium sulfide also with the quantum size effect. And then a very fruitful time started, actually. I mean, during that time, we had many different things we could observe for the first time. So these magic cluster sizes during growth, or highly luminescing quantum dots by surface modification, these type 1 and type 2 nanoparticles, size-dependent oscillator strengths, solar cells, so first solar cell on that time, ion exchange reactions, and things like this were already pioneered during that time. And this is one of these famous pictures, here cadmium phosphide from that time when I was in Henglein's group, here from black to white, actually making these things. So we knew already quite a lot, and looking for these systems. What we couldn't do at that time is looking so carefully to the particles as we can do now. So here is a TM. We would love to have TMs like this at that time. So here, this is now not a quantum dot, but iron oxide. And you can see here the particles. And as all people now in the world, we can make them very monodisperse. And you see them here quite nicely. So we'll have a look to the guy here. And monodisperse, single crystals. Now the crystal lattice planes will show up, faceted surfaces, and almost perfect crystalline structures. So here the iron atoms are seen. So this is what you can do with these modern electron microscopes. And at that time, we just saw, oh, there were so tiny dots, and these were the particles. So actually, something like this we were happy to see as a particle and not as an atom. And even something like dynamics, here is the fusion of gold clusters on a TEM grid initiated by heat. So you see this cluster coming here, and you can see the atoms hopping from one to the other and how a new surface facet is formed. So very nice things which can be done and which promoted this field in a tremendous way. So now we are at the point that we know what we do because we have the analytics, and that was not the case in the beginning. Okay, let's come to particle synthesis. Everything is colloidal synthesis, so you have to mix precursors, and you have the nucleation and growth. And actually, for monodispersed particles, as all colloid chemists know, you have to separate nucleation from growth. And doing that was just pioneering work of Mungi at that time with the hot injection method. Others are pH change and things like this. So actually, you have to control the nucleation and you have to control the growth. We do not know too much about these processes until now, but we learned to make more robust synthetic approaches so that it's almost reliable that we can make now. But there are still some problems in it. Here you can see the synthesis of lead sulfide monitored with a high-speed camera. Now you will see the injection here, and it's getting dark. That means lead sulfide is formed. And you see it's almost quite nice. So almost homogeneously getting black. Beautiful. This is the typical setup, how most people all over the world use it. 50 mils or 100 mils flasks for making these particles. And if you want to use them for some applications, you need more. And this is the same with a scale-up in a 2-liter flask. And the same solution, we inject in the same way, but it's a larger amount, can't do it so quickly. And the same person, so he really tries to inject as fast as possible. But what you see, what you will see here, it's getting black. Here it's getting black. So that means particles are formed. Here no particle is formed. So it's really now a matter of how you mix and how you start, how you separate that nucleation from growth. And this reaction will never lead to monodispersed particles. So what we decided for that reason, something like a little bit more than 10 years ago, to develop a continuous flow system. Because in this case, everything is automatic. So we have precursor solutions, we have pumps, we have some degassing, we have some heating, and we have a mixing chamber where we mix these solutions. This is only for nucleation. Here we have one temperature for nucleation, a steep temperature jump here on the next to a growth oven with a growth temperature here. And then we have spectroscopic online control. We can add different modules here for growing shells on these materials, and that works quite nice. So here's one of these analytic things in the lab scale. So we can produce with these things something like today, it's in the order of 100 grams or so per day, but we can easily scale it up to about 1 kilogram per day, pure quantum dots, depending a little bit on the material. So, and the good thing is, of course, you have then parameters of flow speed and mixing ratios. You see how the quantum efficiency of the particles comes out, how the size of the particles comes out. Everything is in the computer, and therefore there is no human parameter anymore in it. And this you can see here very nicely. So 3 samples here made within 3 months at 3 days, but not one day after the other. Some reactions in between, different reactions in between, different operators, which make, of course, no thing. It's just typing in the parameters in the computer, and but exactly the same. So this is really reproducible, and it works very nice. Interesting things, and I think you will hear more about these in further talks, for example, by Uri, are these dot rods, quantum rods, with an unidirectional growth of a shell, like here. And you can see also with these new microscopes very nicely, if you use energy-filtered imaging, here is the core, and this is the shell. So we have them here in the middle is the cadmium selenide core. Other things like EDX analysis, you can make line scans and you see where is the cadmium selenide in the center and the sulfide at the outside. And of course, what all of us want to use them for is for fluorescence. And there is an application, I think you heard already probably this morning. I just arrived because the train was late. Here, these new TV screens from Sony, the Triluminos, they use quantum dots for backlight illumination. And if you hear to these display people, then quantum dots seem to have really, in the best sense of the word, a bright future for TV applications, for display applications. But I won't talk about these TV applications now. I will change a little bit to the biological application of these things. And you heard already that started in the late 90s with some pioneering work of Paul and Shimon. So the question is, or during the first, when people started doing that, they were rather excited about it because these very beautiful properties of nanocrystals, narrow bands, broad absorption, and things like this. And there was really a boom going on. But for quite a while, it became a little bit frustrating because if you go into vivo, you always end up with rather serious problems. And this is because our body has learned during the evolution process to get rid of nanocrystals in a very elegant way. So we have nanocrystals all around us. We are inhaling them all the time. And if something comes into your body, then a protein corona is formed around the nanocrystals. Then the macrophages come up and they eat them up and deliver it to the liver. So all these very fancy ideas of drug delivery, they stuck for quite a while. We are now a little bit more close to it to get real applications in that. And there are already some serious clinical studies going on. The question was actually how to make a coating for these particles. And the most easiest thing to avoid all these immune reactions is to select a natural transporting system. And that's what we did together with a group at our university hospital. So they were investigating the fat metabolism, and fat is delivered by these lipoprotein micelles. And this was inspired a little bit, or here is a nice cartoon for this type of research, why we want to learn about these fat metabolism. This is a serious problem in Western world, as you can see here. We have a lot of overweight people, which cause serious damages for heart diseases and for diabetes. Okay, so what we actually did is taking these nanocrystals as they are in organic solvents with top topo or oleic acid and incorporate it in the fatty part of such a nanosome, how they call it. So here is one with iron oxide, and you can see it here very nicely with iron oxide or with quantum dots or whatever you want to do. So then this gets injected here into a mouse, and then this is the clinical scan. And afterwards, organ distribution can be measured by taking some biopsies then. And people at the university hospital, they develop very nice techniques then to localize these particles and see how they are. So they take here a small sample of cells. They let them grow in cell cultures. Actually, here are the particles, cut it, and then frozen. Here it's frozen. And now here they are. So one can see here these transport systems in a blood vein, and here are the quantum dots there. So you can do nicely some studies like this. And you can see real-time processes of the metabolism. So here, for example, is a very nice example where they investigated the nanosome uptake by the so-called brown adipose tissue. So this is something quite interesting. All of you know white fat. This is here, what you don't like to have. And there, all of you have a small amount of brown fat cells. They are located here in this region, only a few grams. And they have only one function, and this function is to burn fat. So this is the good fat. And people wanted to see this. That was the first time that they could image it. And the experiment was quite interesting. So here are two mice. One slept in the lab and the other in the fridge. So overnight when it was cold. And so now you can see after injection of iron oxide, here's the time, how it elapsed. This region here in the cold mouse is getting dark. And that means these iron oxide loaded particles are located there within something like 1 or 2 minutes. So here, this brown adipose tissue is working. And that's an experience all of you have. If it's cold outside, you're more like to eat some fatty things as if you are in summer at the beach and someone offers you some fatty products. So this is what you can see here. And then the next thing are these intravital microscopes, so you can look with optical microscopy and now with quantum dot labeled nanosomes into these brown adipose tissue. Here are the cells, small capillary veins, changed to fluorescence contrast. You see here the particles attaching. The cells, they deliver the fat to the brown adipose tissue, and then they inject, after a while, should now inject something here, heparin, which blocks the receptors, and these transporters are released from the surface. So, as expected, how it should be, and this is actually now something, well, if you want to have a take-home message, forget about diet, sleep in the fridge. The next step is, of course, we are interested in other things like only fat metabolism, and we can't use only these natural transporters. So what we want to do is, in this case, to develop a fully synthetic coating of these particles. And that was something where different strategies are meanwhile reported, of course, and you have to get rid of the original surfactants, like top oleic acid or others, and you have to exchange them against others. And many concepts, or one which we also follow, is making some ligands consisting of an anchor group, best with various multiple adsorbing functional groups here, so multivalent attachment, and then some stealth function like PEG here, polyethylene glycol, making new molecules, exchange them at the surface, and functionalize them, somehow conjugate them to antibodies or something like this, and hope you are able to make some delivery. Now, we started with a coating which is similar to what I told you there, slightly a little bit different. That is what Parag's group developed. So where these side chains here interact with these top topo ligands and then form a PEG shell around the particles. And what you see here is a measurement of blood clearance of these type of particles where iron oxide particles were incorporated. You can do the same with quantum dots, of course, also. And they looked here in radioactive labeling experiments for blood clearance times. And here the blood clearance time is something like 10 minutes, not much. And this is within this time, or here within something like an hour, everything is delivered into the liver. And this is not good for targeting. The organ distribution shows up here. Everything is in the liver, small amount in the spleen. This is the typical immune response to nanocrystals. But in this case, there was a lucky coincidence. People at the university hospital, large group of doctors there, they investigated for a long time the autoimmune disease, multiple sclerosis. And this is caused by autoreactive T cells. So that means these are immune cells which eat up your brain. And to keep them under control, the body also produces regulatory T cells. So they are actually the police who takes care that these autoreactive guys do not overdo their work. And these cells, these regulatory T cells, are produced in the liver, in a special part of the liver. These sinusoidal endothelial cells don't care about this work. And you can stimulate this by some glycoproteins, don't care about the abbreviation, so just a glycoprotein delivered to the liver cells will regulate the regulatory T cell production up. But the problem was that they could not deliver it because these glycoproteins are not water soluble, and if these come together, form aggregates, they are no longer active. So the idea was simply to couple these glycoproteins to the iron oxides, which are taken up by these cells in the liver. So we incorporate them there and look what happens. And so people in the university hospital, they did some beautiful results with these. So here is something like a measurement of the development of this multiple sclerosis disease in mice. So here is the time, and these are special mice which develop MS after 10 days, reliably. So here after 10 days, or 11 days in this case, you can see in the moment where you just inject a buffer or unloaded nanoparticles, the score here, that's just observation of these mice when they start to tumble and getting crazy and so. These are these scores, and you see that is a sign the MS disease has developed. Now, if you inject these mice in the beginning, before that starts here, this coupled nanocrystals, no symptoms of the MS comes up. And here also in the second image with the other one, the same. And even if you go to, if you inject after the MS disease has already started, it seems a little bit here in this case that the symptoms go down and that there is a small healing effect. So the people in the hospital, they were really excited about that, and they will start a clinic study with humans next year. Okay, so that is a little bit success rate, but still, this is just by chance. Only a transport system which brings it to the liver where it just ends unspecifically because of the clearing processes by your body. Now, we want to have something which has where we avoid this clearing process, where we have long circulation times. And the way we went in Hamburg for that is we take the particles and we first make a ligand exchange, partial ligand exchange against a small oligomer. And this oligomer consists here, this red part is a small polyisoprene chain with something like 2,000, 3,000 molar weight. And here, this binding group consists of 3 amino groups in this case. So amino groups, a chain with 3 amino groups and polyisoprene. So this is ligand exchanged, still in THF. And then we add a diblock copolymer consisting also of polyisoprene and PEG, polyethylene glycol. And then if you transfer this to water, then immediately a micelle formation occurs, self-organization, of course, and encapsulates these particles which work as a seed for these micelle formation. And then you can cross-link the polyisoprene part radically, and this gives then a very stable shell. And so at the outside, we can also functionalize it with any kind of organic molecules which allow further linkage to something like sugars and things like this. Okay, so here is one of these particles, quantum dot encapsulated. This is the polyisoprene part, and this is the PEG part here. Something sizes 25 nanometers up, depending on the exact size and conditions. One of the good things in this, or one of the nice things of this type of encapsulation is that you can do a very nice optimization of these systems, and you can apply combinatorial approaches. Because if we have this, what we call pre-assembly functionalization, that means we take just a polymer, diblock copolymer, and functionalize this. This you can very easily do, and you can follow your progress by typical chemical analytical processes. So we have partially these functionalized diblock copolymers, and during self-assembly, they are just incorporated here. And so we can mix different types of such pre-functionalized polymers and different concentrations, mix them with non-functionalized ones, and so you can form various patterns of recognition molecules at the surface. And that allows, of course, combinatorial approaches and helps to understand how, for example, multivalent interactions and things like this occur. It doesn't work, of course, for very sensitive materials like antibodies or so. Then you have to do this post-assembly classical conjugation chemistry, but which also is possible to do. Just an example to see how you can easily adjust by these combinatorial approaches the zeta potential by mixing charged and non-charged ligands. And here I show you a brief result how to optimize these systems. It's really, we started this something like 8 years or 7 years ago, and we run into serious problems, very long, also rather low circulation times, until really a very sophisticated optimization of all this encapsulation process started. And one thing of these optimization was also variation of the polymer block lengths. And you can see here, these are uptake studies in cell cultures, and we used diblock copolymers with different molar weights. So here is a rather small one, 4,500. This is 100 monomer units approximately, and then a little bit more here, 8,000. And what you can see, so it's a little bit light here, there is unspecific uptake by the cells. The blue one is the cell nucleus, and the red dots here are the quantum dots. So larger ones also here, 8,000. Here, 14,000, you can't see it because of the illumination, but here with 14,000, there is no uptake anymore. And it's really starting from 10,000 or so molar weight until this value. This is an optimum value for the size. And by coincidence, one can also see this kind of similar thing in fluorescence quenching experiments. So the idea was actually, if we have shielded the nanocrystals, then also biology should not see what is inside. And so we said, can we somehow correlate the biological response with some physicochemical properties? Because that makes it, of course, much more easy to see something than in cell cultures. So whether this is really a scientific causality or so, I don't know. But the idea actually is, if something is shielded, biology will not react to these nanocrystals which are inside. And here are fluorescence quenching experiments with these different molar weight molar weight coatings, and we add copper ions, which are very effective quenchers if they reach the surface. One copper atom is already sufficient to quench the fluorescence completely. And this behavior is seen in pure quantum dots. If you have just quantum dots, you add copper, you add almost nothing, and there is no fluorescence anymore. But however, with the polymers, it's getting better. And these polymers here, where we still see quenching, there we saw also some unspecific uptake. Here, where we don't see almost any quenching, we do not see unspecific uptake. And you can play around with these systems quite nicely if you look more in detail about the lifetimes, whether it's static or dynamic quenching. You know a little bit about whether this copper penetrates through the shell or comes to a special distance and things like this. So that you can do quite nice things on that also about energy transfer and things. So with the good particles, we finally end up having rather inert nanocrystals. This is here, these are the particles after 2 hours, after 20 hours in serum-free medium, after 22 hours, after 20 hours with the PEC-OH here at the outside, you see some unspecific uptake, but 20 hours without serum, then the cells are really starving. They're eating up everything. Here with the amino group, no uptake, and with serum, also no uptake. These are the commercial ones. And you see the red dots here already. After 2 hours, you have unspecific uptake. You can't use these things for specific targeting because any type of cell eats them up. And so here is an example also taken by our colleagues in vivo microscopes for 24 hours, observing cells in the presence of these encapsulated particles. You see cell proliferation. Everything is fine. The cells do not care about the quantum dots. Here, some quantum dots come around. So you see some in the focus here, some red, but the particles don't care about that. That's how you want to have it. Okay. And here, finally, this is then in vivo with these systems. And this is the liver. These are images of the liver with optical microscopy. And you can very nicely see how these particles circulate through the capillary veins of the liver, here in fluorescence mode also, and they are not uptaken. So we have circulation times calculated from MR experiments with iron oxide encapsulated, with encapsulated iron oxides of a day and even more. So these are then the systems which are feasible for targeting, and here is some work on targeting of a tumor. You see here with SPIOs, again with iron oxides, so with MRI, here is the tumor, no targeting, and here with the antibody-coupled ones, you see some targeting. However, this is far from being good for clinical applications. We just can decorate the tumor, the outside of the tumor. We did not penetrate into the tumor. Here it's just tumor adhesion. So not for the therapy, finally. So at the end, I will just give you a few images of some trends, what is future in this field. One is these multivalent binding. So the idea, what people did in biology first, or when applying that, they said, okay, let's take just an antibody. The antibody does the biology, and our particles do the imaging or delivery or whatever. This is, of course, not enough. I mean, nature is much more complicated. If you look how a virus works, or for example, this is not simply just an antibody or one recognition. There are various processes which you need to combine. The charge, then the small adhesion, this adhesion to cells, these rolling on the epithelium and things like this, and then finally the uptake and the delivery into the cell and doing the job at the place in the cell where it should need it. But that means you have to use multifunctional interactions, so you have to add many different things. You have to also take advantage of these multifunctional bindings with low binding constants, actually, but with multivalence that works finally. For example, sugars play a big role. Here are some examples where we have specific uptake of sugar-decorated particles. Others is multifunctional particles. Here, for example, iron oxide with quantum dot quantum rods. This is not so easy because iron usually quenches the luminescence. We can see here in single particle microscopy images that in this case, where we apply a two-step encapsulation, first iron oxide with a small polystyrene shell, and then in the next step, these quantum dot quantum rods, then the luminescence is still retained in these systems. Or making a little bit more fancy structures here, also the geometry of these systems is interesting. It resembles more like a virus with all these things there, and you have plasmonic and iron oxide. Or you use controlled clustering for MRI experiments. Here, one particle, and you aggregate them within one of these capsules, yielding then to differently sized particles. As you can see here, these type of raspberry structures, and they have very interesting properties in respect of their sensitivity in MRI experiments. So if you plot the hydrodynamic radius of these clusters against the sensitivity, the relaxivity as it's called in MRI experiments, then you see that at a given size here, you get an optimum where you have something like 20 or 50 nanocrystals aggregated in these particles. Here are some theoretical curves. The theory is not very, very well in these systems, and these are different times then, and so. But in principle, theory predicts an optimum in size with an optimum number of particles there, and you can really realize this by controlled chemistry. So I will leave you with one of these videos I like to present in the end when I thank all my co-workers. So that's the vision, how we want to proceed, of course, to encapsulate whatever we want into these transporters, to add some biological recognition molecules, and to inject it into your body, and then the systems find their way. Here, as you can see, actually, I showed these videos always to the politicians who gave money, and that's much better than many other things. So here you see they specifically bind to a tumor cell in this case, and then they undergo endocytosis and release some drugs. Of course, you can use all these capsule techniques. And finally, you can remove the particles out of them. We do not need the particles. We can do everything with hollow capsules and encapsulate whatever we want. And then finally, you're healthy again. So fine, that's our vision. Thank you.